And there we go, recording started. So, okay, yeah, hi everybody, welcome to the Welsh Azure User Group virtual meetup on the 30th of August 2023. Thank you everybody for coming along or rewatching on the video, whatever you're doing at the moment. Yeah, great lineup again for you tonight. So we'll just get into it pretty quickly. So just as usual, you know, big thank you to you all from the people that obviously organise all the Welsh Azure User Group meetups. As always, this is a local user group for people that are interested primarily in technology surrounding Azure. But please do feel free if you've got any ideas, you've got any sessions you'd like to see, or you'd like to speak or get involved at any point, please reach out to one of us. There's all our contact details. If we're not already following each other on LinkedIn or Twitter, please do reach out and say hello. Like I say, thanks for joining us from the team. Like I say, there is a good lineup, a bit of a mix of talks tonight. We've got Johnny Hooeyberghs joining us to talk about that wonderful area of Azure Quantum and specifically around Microsoft Q Sharp as well. So really, you know, I personally find these subject areas really fascinating. So really looking forward to Johnny's session there around quantum and where we are. We know it's been talked about for the last few years. So yeah, looking forward to seeing where we are and understanding what the latest point is from Johnny. So looking forward to that in a second. And then thank you to Leo for joining us as well. He'll be joining us a little bit later on the second session, talking about how we can run PowerShell with the Azure Deployment Scripts. So again, really kind of intricate, you know, useful information for you guys, you know, if you are, you know, in that space, admin or automation world. So, you know, really looking forward to Leo's talk in a little while as well. So thank you to Johnny and Leo for joining us this evening, giving up their time to kind of impart their knowledge on us. Timings wise, we'll kick off shortly now with Johnny and the Azure Quantum talk, about 45 minutes. So around about 7:30, maybe a little bit earlier, we'll be over onto Leo's talk. As always, please do stick around for the quiz. So roughly speaking, around about 8:15. It's a little bit of fun, a few questions. If Matt's quiz making skills or anything to go by, they should be a good bit of knowledge and fun in there. So got a couple of Amazon vouchers obviously to give away on that as well. So it's worth your while sticking around and get your name in that quiz. So yeah, looking to kind of close out in around about that 2-hour window. So that's our timing. So as usual, few quick housekeeping rules, please everybody. Do be courteous to each other. Should go without saying. There are no silly questions at all. We are all here to learn. Nicholas being pessimistic with the quiz tool, Matt. Come on, we'll have to sort that out.
Oh,
No. But no silly questions. We're all here to learn. It's a community user group. Ask away. Please do stay on mute unless you're invited to come off and speak off mute. But yeah, you've got control of your own camera and microphone feeds. But obviously, please don't come off mute and put the speaker off unless you feel you have to for whatever reason. Use chat facilities. Any questions? We'll keep an eye on the chat room. Any questions? Drop them in there. We'll see if we can get an appropriate time for the speakers to answer them if they know them. And yeah, feedback. Finally, any kind of feedback you've got, I'll drop a QR code at the end of the chat. Please do give us some feedback. Let us know how you felt the talks were. Again, whatever sessions you're looking that you'd like to get a bit more information on. We really do use that information to try and get some relevant talks on that will be suitable for our community. So yeah, and finally, please do join the quiz after Leo's talk around about 8:15. But finally, we are here to enjoy. So please do be interactive and enjoy the sessions. Take part in the chat. Before we kick off, just a quick shout out from both our sponsors, as per usual. Servant have been with us since the start of the Welsh Azure User Group. Really is, appreciated the support that all our sponsors have given us over the years, but specifically Servant have been with us from the start. Big shout out to those guys. As you can see, they sponsor a number of UK-based user groups, so they're doing their bit for the Azure community. So kudos to those guys, and go and check them out if you haven't heard of them before, or you're in need of a pure play Azure Microsoft partner. And likewise, our more recent partner is CreditSafe. Obviously being the Welsh Azure User Group, CreditSafe have got a HQ based in South Wales in Cardiff. So really great to have support from that team and those guys over there. really to support. And like I say, our mission, one of our missions was to try and get a network of IT professionals and developers kind of communicating across the local business community in South Wales. So obviously COVID set us down the marvelous path of being a bit of a global audience joining, and of course we don't want to lose that global audience as well. So the choice is upon our shoulders to try and make that a bit of a hybrid if we can, and build up that community even more. But like I say, big shout out, thanks to Servant and Credit Safe for being sponsors of the user group. It's really appreciated. And on that note, I'm going to be quiet, and I think we'll kick off a few minutes early, and I'm going to hand you straight over to Johnny, and we're going to get on with the good stuff and hopefully get some good learnings out of it. So yeah, thank you again, Johnny, for joining us. Hope you're well. I'll hand straight over to you.
All right. Thank you for the introduction, John. And so, yeah, good evening, everyone, and thanks for having me. I'm really enjoying these kinds of user groups and sharing my experiences with like-minded people, let's say. So I'll dive right into it by sharing my screen, because I've prepared a little presentation. So that should be it. Yes.
Yeah, got you.
All right. So indeed, today I will talk a little bit about Azure Quantum and Microsoft Q Sharp. I will explain in just a minute why I'm doing this. With this slide, this next slide, I'll talk very shortly about myself and what it is that I do. So my name is indeed Johnny. I'm from Belgium. I'm a software developer and consultant, doing mostly development in the Microsoft space, in the .NET space, and in the Azure cloud space. So I'm not really doing quantum computing professionally. I already discussed this a couple of minutes ago with John. I was at a conference many years ago looking at a presentation from Microsoft about the quantum computer that Microsoft was building. And there was so much information in a very short time, only 1 hour session. But I was very intrigued, I was very interested. So I decided to dig a little deeper myself. I spent basically the whole summer reading books, looking online, trying things out, and really diving deep into this topic. And then from one thing came another thing. I basically spend a lot of time looking into the quantum stuff, experimenting with this, and also doing presentations. And that is what I'm doing today. I just want to share my experiences, the things that I've learned as a software developer. So my goal is not to blow you away with mathematics or with physics, because that is also not my background. My background is purely in software development. So I really want to talk about quantum from the perspective of a software developer, let's say. So yeah, everything that I've prepared for today is available online on my GitHub page. So in the bottom of each of my slides, you will see a link to my GitHub page, and it has a very specific repository for tonight. So there's the Azure Quantum and Q Sharp Welsh or Azure User Group repository. And it contains a copy of this presentation, and it also contains all of the examples and even more examples than I can talk about today. So the QR code will also bring you to the same page. Let me quickly show you. So here, if you go to GitHub/Johnny, which is my nickname, you will find an About Me section. And then if you scroll a little bit down, you will find an overview for all of my presentations and events for this year. And here in August, there's the Welsh Azure User Group. If you follow that link, you will get right into the repository containing examples and, of course, the slides in the bottom here where we are going to talk about today. So I will start with showing you a little bit of theory. I told you, I promised you there wouldn't be any math or physics, but there should be a minimum amount of math and physics in order to understand what quantum is all about. So don't be afraid of the things that I will show you. Try to follow. And if there's any questions, I have the chat open on my second monitor right here. So I will look at the chat very regularly, and I will try to answer your questions immediately. So you don't have to wait until the end of the session. If there's any questions, just write them down in the chat, and I will try to answer your questions right away, immediately, basically. Cool. So whenever I tell the story about quantum computing, I always start with a little story from when I was attending high school. And the reason I want to tell this story is because for me, this is basically why we need quantum computers. So many years ago, when I was still a teenager, I was attending school and I was in a technical school, and we had a class where we had technical drawings. This has nothing to do with quantum computers, but I was finished with my exercise a little bit early. And the teacher knew that I had a little hobby at home. I was doing programming. So as a teenager at home, I was writing very small DOS computer programs using the help from my mom, because my mom was into QBasic and Turbo Pascal. She was doing a little programming and she taught me how to do it. And I was really, really happy with that. I was playing around and the teacher knew this. So the teacher came up to me. He said, "You are finished with your exercise. I have a little challenge for you." And he said, "Do you know what chess is? Do you know what a chessboard is?" So here in this slide, you can also see the chessboard my teacher was talking about. So a chessboard is based out of 64 squares, 8 times 8 squares. And there's different pieces on a chessboard. And there's one piece in particular, which is represented by the horse. I think it's the knight. And it can do very distinctive jumps. So on the left-hand picture, you can see that the horse can actually move to 8 possible positions. It basically jumps 2 squares forward and then 1 square to the left or the right. And it can do this in all directions. So it can also jump 2 squares to the right and then 1 to the top or 1 to the bottom. And this is what we call the horse jump. So from that starting position on the left-hand side, there's 8 different possibilities. So the teacher told me, "Can you write an algorithm that starts at a random location and tries to jump around the chessboard and visit each square exactly 1 time, and so fill up the entire chessboard?" And I was like, "Yeah, that's easy." But I was still a teenager, so I didn't know about these very cool programming features like recursion. So I basically did for loops. So I wrote 64 for loops nested within each other in order to make my horse jump around 64 times. And the reason it's 64 for loops nested is because when you make a wrong jump, or when you make a jump that basically locks you up because there's nowhere you can go next, because all of the 8 possible locations for your next jump have already been visited, you need to backtrack. So you need to do a step back and try something different. So I wrote this algorithm and I thought I finished it, and I ran my application, and it ran for seconds, minutes, even hours, and it wouldn't finish. So I thought I made a mistake. And I tried multiple times. I tried rewriting my algorithm. I tried some debugging. I tried all kinds of different things. But I was a teenager. I got bored with it, and I just went and played outside. And then I forgot about this whole problem. It was only when I was in university that this problem came back to me. And it's called the night tour. And the reason it's a problem is because it's actually quite complex to solve it, because there's so many different possible routes. There's so many jumps that you need to take in order to brute force a solution to this problem. And this is the first time that I got introduced to the concept that a computer, even though it is very, very fast, cannot solve all of our problems because it's actually not fast enough. And that is why we need quantum computers, because we still have problems today that we cannot solve with a classical computing algorithm. Unfortunately, I don't have the solution for this problem in quantum today. To be honest, this problem is just a very small example of a possible problem. It can actually be solved by a classical computer quite quickly if you do a couple of things right. But that's not the story I wanted to tell. The story I wanted to tell was it can be quite difficult, and I struggled with this when I was a teenager, and hopefully quantum computers can help us to solve some of our problems that we are still facing today. Now, what is quantum computing? Well, it is based on quantum mechanics. So quantum mechanics is a field in physics that specifically targets the very small particles and objects that exist in our world. Now, quantum physics or quantum mechanics is a field that actually where the first things happened 100 years ago, like 1910, 1920, 1930. Those years, a lot of scientists were very active in researching the field of quantum mechanics, which means, again, the behavior of particles on a very, very small scale. And a couple of scientists really wanted to create laws that describe whatever is happening in our universe, and they saw that things on a macroscopical scale, like the scale we live in, like chairs and a ball and things that you see outside, behave very differently from the microscopical world. So very tiny particles like atoms and even electrons and things that are even smaller than that they behave completely different than we are used to. So it's very hard to create a science, to create rules that are applicable both on the microscopical world and the macroscopical world. And when scientists were looking at this microscopical world, they saw phenomena that were very hard to describe, and very weird things happened. And now, 100 years later, we are actually understanding some of these phenomena, and we are trying to even leverage them and use them to our advantage. In this slide, I have two examples of phenomena that we can use in quantum computing. On the left-hand side, there is a drawing of what superposition or quantum superposition can be. It's not what it actually looks like. It's just a drawing that I did, which represents what it could look like. Superposition actually means that a property for an object can be in multiple states at the same time. That's not entirely correct, but let's call it at the same time. For example, an electron has a property called spin, the spin of an electron. It's not something that we can visualize. It's just a conceptual thing. It's to do with the amount of energy that the electron has, but it has a spin property. And the spin property can have two distinct states. It can be up or it can be down. And those two distinct states can be thought of as like a Boolean value, like a bit. It can be up or it can be down. It's true or it's false. Now, in the quantum world, it seems that a property can also have the two states at the same time. So it can be up and down at the same time. So you can see in the schematic that if you do up plus down, you have up and down at the same time. And that is what superposition actually is. It is a very weird phenomenon because we don't know anything in our world, in our visible world, that acts like that. What's even weirder is that when scientists do an observation or they do a measurement on what is the value for this state, and that state is in superposition, it loses its superposition and it immediately picks one of those two distinct states. So scientists are able to see this happening. So they see when they do a measurement or when they do an observation that the superposition collapses, as they say, and it chooses one of those distinct states. And that's actually the reason why I told you it's not really at the same time. Basically, the value, let's say, for that state is not yet known. It's only known when you observe it. So only when you look at it or only when you measure it, the universe makes a decision and says, okay, it's going to be up or it's going to be down because now you're looking at it. So I need to make a decision. That's the idea. Very, very weird, but this is what actually happens. And there's always the same joke that I make. It's a little bit like a USB slot, like the old school USB-A. I don't know if you know what a USB-A looks like. If you want to plug that into your computer, it will never fit. You turn it upside down a couple of times and it never fits. You first have to look at the USB port to see how it's oriented, and then you see, okay, I need to orient my USB key up, and then it fits. That's the same thing that is really happening on a microscopical level. Whenever we need to measure something and it's in superposition, it will jump into one of its distinct states, and that is called superposition. This is very cool because this means we can, just like with bits, which can be encoded in tiny little switches. We can also encode something into a superposition state, and that is something that can really be useful in computing, quantum computing. Now, another phenomena is the entanglement. So scientists have proven that when one particle has a property that is in some kind of superposition, there can be another object that has the same property also in superposition, and those two objects or particles can be entangled in some ways. And the entanglement means that if you observe only one of the two particles, it will make that choice. It will make that decision. I'm going to, for example, if it's an electron, I'm going to have a spin up. And then the other particle that was entangled with the first particle that you observed will also collapse its superposition state, and it will always have the opposite state, which is very weird. And there's very, very cool experiments executed where even the two particles, they don't need to be close together. They can be very far apart from each other. And then when a scientist observes one, the other one will collapse to the opposite state always, which is mind-blowing. These are, again, phenomena that we know exist. We know that they work. We can leverage them, so we can build systems on top of those phenomena, but we can't explain them. We really can't tell why they are happening, which pisses some scientists off, but other scientists, they say, well, it is what it is. Experiments have proven that it actually works like this, so we can just use that to our advantage. For example, the experiment that they did for the entanglement is creating entangled photons. So photon, the elementary particle of light. So they created that on a satellite orbiting Earth, and they were able to split particles where you have two entangled particles, and then they would use laser beams to send one to a laboratory in China and the other half to a laboratory in Austria, and then do these experiments. And even when they're so far apart, they would immediately collapse to the opposite states, which is just, again, mind-blowing. This also means that there's no communication between those entangled particles. It's not like they're talking to each other or calling to each other via radio waves or whatever, because it happens instantly, really instantly. There's no delay, so there's no communication because nothing can communicate faster than light. So we really have no clue, we have no idea how that works, which is, again, very, very, very cool. There are theories about wormholes and stuff like that, but when science goes into science fiction, that mostly means that we have no clue what's happening. So yeah, these are two of the very important phenomena from quantum physics that we are going to leverage in quantum computers and hopefully build algorithms on top of that. Of course, I'm already talking a long time about these very weird things, but why should we use these? Why would they help us? Okay, let's go back a little bit and let's go, why do we need quantum computers? Now, I told you before, there are problems that we cannot solve today because they're just too complex for classical computers to solve. I have a list here: security, communication, drug development, AI, and machine learning. These are not per se problems we cannot solve, but problems that are difficult to solve or even unable to be solved because when we use them in such a big format, it's just too difficult to solve. Security is a very, very nice example. Security is not a problem that we cannot solve. It is a problem that we have created because we don't want it to be solved. We create public and private keys, and the reason we create them that they cannot be solved is because we don't want security to be broken. So security is a very good example. If you dumb it down a little bit, the public-private key encryption works based on the fact that when you take two very, very large prime numbers and you multiply these prime numbers together, you get an even larger number. And this is an operation you can only do in one direction. You can only do the multiplication of the two very large prime numbers into the larger number. But a computer has a very hard time doing the opposite. When you feed the very large number into your computer, the computer has a hard time factorizing the original prime numbers because it basically needs to brute force. It needs to just try to multiply all the prime numbers together until it by accident gets your very large number, which is something that a classical computer or even all classical computers combined will take thousands of years to do. Computers are just too slow for this. Another example is drug development. If we want to create a drug and that drug needs to cure a disease, we are not able to create a complete simulation of that drug on the human body because the human body is too complex. There's too much going on. There's too much interactions between small particles, and we don't have the resources to put the whole system of a human body into a computer and then do a simulation where we introduce a drug into that system. And that's also the reason why we still do animal testing, because we create a drug based on ideas, based on little experiments, and we hope that things will work out. So we test it on an animal. If the animal, for example, the rat, dies, we know that we made a mistake and we need to try again. Just because we can't have a computer simulating the entire human body. Again, a problem that we cannot solve today because it's exponential in nature. That's basically the idea. When the human body was something very simple, we could do a simulation. But we have so many particles working together that the problem becomes exponentially large. There's an exponential amount of variables that we need to work with. And then all the different possible routes are too many to all work out. And the problem is too hard to solve. We basically have the same with AI and machine learning. There's a lot about AI and machine learning today. There's a lot of hype around that, with and that's a good thing because it's very cool what we can do today. But in order to create a perfect AI system that immediately knows a reaction to all of our problems, we basically need to train a model for an infinite amount of time. So the AI we have available today, we have models trained for a period of time, and those models are never perfect. They can help us, they do good things, but they also do bad things because they don't know anything, everything. So in order to make a perfect AI, we need an infinite amount of time to train those models, which we of course don't have. So again, quantum computing could also help us with that, because quantum computing, as you will see a little bit later, should be good in solving exponentially large problems. And then, of course, communication is a little bit different. We don't really have problems with communication today. The only thing we have problems with in communication is people listening to our communication and basically stealing the things that we are communicating. This is also something that quantum computers can solve for us, and I will get back to that in a couple of minutes. Okay, so now we know what an exponential problem is. We know that these exponential problems cannot be solved. We know the different areas where these exponential problems live, and we hope that quantum computers can solve those problems based on the quantum physics phenomena that I just described: superposition and entanglement. Let's look at classical computers. A classical computer is a very simple thing. It can only work with bits, and a bit is a value that can be 0 or 1. So it's two distinct states, 0 and 1. We're probably all developers, so we all know what a bit is. Now, we also know that if we want to represent data, we can combine these bits, and we can decide ourselves the protocol. So we can decide if we put bits this way, we can represent a video. If we put bits in another way, we can represent pictures or text or whatever. But we can combine bits in order to represent all kinds of data. Now, in the quantum world, quantum computing world, that is, we will do the same thing. In the quantum computing world, we will also work with those two distinct states, 0 and 1. I told you about superposition. I told you that, for example, the spin of an electron can be in superposition of its two distinct states, up and down. So we can basically translate up and down to 0 and 1. We have a binary Boolean state. Very nice. In the quantum world, we can also combine these bits into representing data, quantum data, just as in the classical world. So we, as developers, don't have to learn a completely new thing. We are going to base ourselves on the same concepts from classical computers: bits and data represented by bits. Now, things become interesting when we introduce superposition, because when we introduce superposition, for a very long time already, it is proven that superposition is actually a linear combination from linear algebra between that 0 and 1 state. When I told you before that superposition state of two distinct states is being the two states at the same time, that was incorrect. That's incorrect. We basically have a function like you see here that describes the possibility of the state being 0 or 1. So it's not going to be 0 and 1 at the same time. It's basically just like a theoretical state of the amount of percent that when you observe it, it's going to collapse to either 0 or 1. Very, very weird. And it's not theoretical. I told you just now it's a theoretical function. No, it's in the physical world, it actually works like this. When you do an observation for the state of a property of a tiny quantum particle, when you observe it based on this function, the universe will decide if it's going to be 0 or 1. And the cool thing, we can actually change that state. We have tools today where we can shift those probabilities from being more to the 1 side or more to the 0 side. And that is the power of quantum computers. And I will come back to that in a couple of seconds. But you just have to remember that it's not going to be 0 and 1 at the same time. It's a linear combination that describes the probability of it being 0 or 1. And now there's going to be a little bit of math. So I'm very sorry. You don't have to be scared. It's high school level math, a little bit of linear algebra, but it's quite simple to understand, to comprehend if you just follow me. So if we look at the alpha and beta values, we can describe them in the following way. If we do alpha squared plus beta squared, the result always needs to be 1. So this is the normalization for our linear combination. And what that means is that together, they are always 100%, always. So 1 means 100%. So we always have the combination of alpha being some value, beta being some value, and together they are always 100%. So it can be 50-50, which means if you observe it, you have a 50-50 coin flip chance of it being 0 or 1. But it can also shift both directions. So it can have a higher probability of being 0 or a higher probability of being 1 based on this little formula. Now, because mathematicians are weird people, they decided that alpha, they didn't decide, but they needed to be alpha and beta to be complex numbers. So A plus BI or C plus DI, which means complex numbers. And the reason for that, I will explain in just a second. Now, when we look at perfect superposition, 50-50 coin flip superposition, because alpha squared plus beta squared needs to be equal 1, these are basically your mathematical representation values for a superposition state. So 1 over square root of 2. Why? Because we needed to square alpha and beta. And 1 over square root of 2 squared is half. Half 0 plus half 1 equals 1. So now you have 50-50. That's the idea. The reason I'm telling you this is because this is actually the most important part about quantum computers. If you want to work with quantum computers, you have the classical part of being zeros and ones and combining zeros and ones into data, but you also need this part, because when we want to have a qubit or a quantum bit in superposition, we need to be able to write down what the current state is. And in order to comprehend that, you need to have that mathematical representation of the values, the probabilities of it collapsing to 0 or 1. So that is very important to know. And with Boolean logic, that is very easy to do from the top of your head. You know that not true equals false and not false equals true. That is very easy. But these kinds of mathematical expressions are a little bit harder to do from the top of your head. So we need the math to be able to write it down and to do it. Now, later in this presentation, I will show you a programming language that Microsoft created. Microsoft created the Q# programming language to write quantum programs. But you can run Q# applications on your local machine, which is not a quantum computer. It's a classical computer. Now, the reason it works, for very small problems that is because what Microsoft is doing in the debugger for Q#, it's just running all of this math. So it stores these mathematical formulas. And then when you do things in the quantum world, it just does the calculation. So the debugger will just do all of the calculations in order to know what the percentages of collapsing to zeros and ones are. So the math, again, is very important. Now, to make it a little bit more easy to understand what superposition actually is, there is a scientist that introduced this sphere, or the block sphere. Maybe you remember from linear algebra in high school. In linear algebra, when you have a linear combination like this, you basically describe a vector in a three-dimensional space, in a vector space, that is. Now, this sphere is nothing more than the vector space that describes the superposition state vector of a qubit or a quantum object. Again, this sounds completely out of whack, but it's actually very easy. Follow me. This is a unit sphere. A unit sphere means that you have a center point, you have three axes, x, y, and z, and then you have a vector that points from the origin, or for where these axes meet each other. From that point, it goes towards the edge of that unit sphere, and the length of that vector is always 1. And that 1 is actually the 1 from the normalization formula here. So this 1 is the length of your vector. Now, when your vector points somewhere in this sphere, it basically describes what the superposition state is. And when we look at those two distinct zeros and 1 states, 0 will be straight up the z-axis. So when the vector points straight up, that is going to be 0. But when the vector points straight down the z-axis, that is going to be 1. So now we have those two distinct states. Everything in between, the infinite amount of possibilities that this vector can point to between 0 and 1, is some kind of superposition. And it's actually easy to calculate what the percentages are if you know your trigonometry. Because when you know your trigonometry, you know that you can draw these little dotted lines from the point where the vector points at to the z-axis and to the y-axis, for example. And those dotted lines show you what the percentage is of the vector collapsing to either one of those two axes. And you can use sine and cosine to calculate, based on the angles, to calculate those probabilities. Very cool stuff. So from this picture, you probably already understand that if this vector, which is called psi, so it's an arbitrary superposition state, psi, when it points here, the chances of this vector collapsing to 0 are higher than it collapsing to 1. Why? Because it's closer to 0. The distance it needs to travel to collapse to 0 is smaller than it needs when it's collapsing to 1. So this is basically all there is to superposition. It's just a vector within this unit sphere. Block sphere is what this sphere is called. And you can immediately see with your own eyes that the chances of collapsing to 0 or 1 are higher or lower depending on the orientation of the vector. So very easy. And we can do the same thing in code or in mathematics by just calculating using trigonometry, sine, cosine, stuff like that. Of course, it's in a 3D sphere, so it's a little bit more complicated. You have complex numbers with that. But if you dumb it down a little bit and you go two-dimensional, then it's even more easy, because now you just have your regular trigonometry. For example, on the left-hand side, you have that vector pointing horizontally, which means a super 50-50 superposition, like an equal superposition, a coin flip, and your angles, as your values, as I showed you, is 1 over square root of 2. Now your angle is pi over 2 radians, so it's like 90 degrees. And if you do your sine and your cosine for pi over 2, you get as a result 1 over square root of 2. If you have another angle, for example, 2 pi over 3 radians, and you do a cosine and a sine of this, you will get 1 over 2 and square root 3 over 2. So you can just very easily calculate what these angles are. So yeah, enough with this stuff. This is just all the things you need to know in order to understand what superposition is, how we can describe it mathematically, and how we can calculate the result in a simulated environment. Now, where the hell does the power come from? Why can a quantum computer be more powerful than a classical computer? Well, because of this superposition. Think about it. When you have one single qubit or one single quantum bit, you have two states at the same time. Again, that's not entirely correct, but you have a linear combination that describes two states at the same time with some kind of percentage. Now, the states are 0 and 1. If you add a qubit to your system and you have now a 2-qubit system, you basically have 4 values that you can represent at the same time. You have 0, 0, 0, 1, 1, 0, 1, 1. So 2 qubits that are both in superposition combined, when you do a measurement, you have a random result that can be one of those 4 values. So it basically represents those 4 values again at the same time. Now, the power for quantum computers comes from the fact that when you keep adding qubits to your system, the amount of state that you can represent in superposition doubles. So it's an exponential thing. So 3 qubits will give you 8 states at the same time. 4 qubits will give you 16 states at the same time, and so on. And it's already proven that there are very specific algorithms that we can write in the quantum world that leverage this superposition. And the fact that adding 1 qubit to your system doubles the power of your system makes it exponentially powerful. Just like we have problems that are exponential in nature and grow exponentially when we add more difficult variables to the system. Now, when you look at classical hardware, when you look at a classical CPU, when you want to double the amount of power, you need to double the amount of transistors inside. So you need to create a chip that is twice as big, or you need to create 2 chips, or you need to create a chip that has transistors that are half in size. So you can fit double the amount in the same chip. Now with quantum computers, you only need to add 1 single qubit to your system in order to double the power, which is crazy. That is the good news for quantum computers. The bad news for quantum computers is when you add 1 single qubit to your CPU or quantum processing unit, 1 single qubit added, you make it exponentially more unstable. And that is the problem we are still working on today. So the quantum computers today, they work with a small amount of qubits. A qubit will be represented by some kind of quantum particle. It can be the electron that I told you about. It can be the spin of an electron that's being used to encode bits into. So bits that can be 0, bits that can be 1, but also can be in the superposition state. So when we have 5 or 20 of these electrons, we can use them in a chip to do quantum calculations. But again, when we add 1 single qubit to that system, it becomes more unstable. Why does it become more unstable? Because superposition is very hard to keep. If you put a particle in superposition and something interacts with your particle, it loses its superposition because it comes into reality and and the universe needs to make the decision if it's going to be the 0 or the 1 state. And that's the problem, because nothing in our world is completely free from interacting with the rest of the world. There is things like air, there's things like radiation, there's things like temperature, heat. All of these things influence these tiny particles very heavily. So it's very hard for us to keep these particles stable and in a system that keeps all of these things away from it. And that is also the reason why today quantum computers are very cool. So they keep them at almost absolute 0 in temperature, and absolute 0 is not 0 Celsius or Fahrenheit, it's 0 Kelvin. So it's like 0 absolute 0, which is minus 200 or 300 degrees Celsius, which is crazy. So we need to use a lot of power in order to keep those systems very cool, because heat makes particles vibrate, and when they vibrate they can hit each other and they lose their superposition. But we also have radiation from space that is hitting us continuously, so we also need to build these laboratories that can shield all of that radiation. So it's very, very hard to build a physical quantum computer. And again, adding qubits to your quantum computer just makes it more unstable, because now you need to make it more reliable. But I will talk about that in detail in a couple of minutes. So what does a quantum algorithm actually looks like? Well, there is It's basically the same as with classical computers. So with classical computers, we are creating algorithms based on circuits. So you probably have learned this when you were in high school also, that a CPU is basically built out of these logical gates. And these logical gates, you can put bits through those gates, and then you change the bit values, the Boolean values, basically. And you can combine all these gates into circuits. And the circuits are the base for all of the operations that a CPU can execute. So a CPU has multiple functions that are built into it, and we can use those functions to do calculations. And again, those functions are built out of gates into circuits. Today, of course, we are not building those circuits and ourselves. We are using high-level programming languages that basically have a couple of layers, and eventually they will call into these functions from our CPUs, and the CPUs will call into the circuits. So that is the layers that live between the high-level programming languages that we use and what actually happens in the CPU. Now, for the quantum computing world, we do exactly the same thing. We build circuits out of gates. Only these gates are going to be different. There's going to be gates specifically targeting quantum bits and changing quantum superposition states. And these circuits are things we can build. And then on top of that, we can build programming languages that call into these circuits, and we can build algorithms in that way, basically. What you see here is an example circuit of a teleportation. So in the quantum world, we have a very weird property, that is that you can never copy a state. So in classical computing, when you have data, you can very easily copy that data into another piece of your memory, for example. In the quantum world, that is not possible. When you have a superposition state, you can never copy that state into another qubit to have the same superposition state. The only way to get the same state in 2 qubits is to do the same operations twice on those 2 qubits in order to reach the same superposition state, finite state, let's say. So you can never copy. A thing that you can do, however, is teleportation. You can teleport state from one qubit to the other qubit, and it sounds like copying, but it's not. Teleportation is not copying, because with teleportation, you basically destroy the state from the origin. So when you teleport from one qubit to the other, the source qubit will lose that original state. You just teleported that state to another qubit. And this is the circuit that does it. It is actually quite a simple circuit. We basically have 3 qubits on the left-hand side, and then we have 3 lines, horizontal lines, and those 3 horizontal lines represents the state of that qubit on a timeline. So the timeline starts at the left-hand side and travels to the right-hand side. So we have 3 qubits. The first qubit is the source qubit that contains the state or the message. And then we have 2 additional qubits, 1 qubit that needs to use the source, and then the second qubit that we will use as a destination. Now, you can see a couple of gates here. The first gate is the H gate, and this is one of the most important gates in the quantum world. It's called the Hadamard gate. And the Hadamard gate puts a qubit into superposition or takes it out of superposition. So in this specific case, this second qubit is in state 0, the 0 finite state. So it's not in superposition, it's just 0. When we put that through the Hadamard gate, it puts it into a perfect 50-50% superposition state. So now it's 50-50. And if we observe it, it will collapse to either 0 or 1. The second gate you will encounter here is a gate that is on 2 qubits, and that is the C-NOT or controlled NOT gate. It's just like a Boolean NOT. Basically, it flips the target qubit from 0 to 1 or from 1 to 0, just a NOT, basically. It flips it only when the source qubit is 1. So only when the top qubit is 1, the bottom qubit will be flipped. And here things become very interesting, because the top qubit is not 0 and it's not 1. It's both at the same time. Or it has not yet made a decision. It's in superposition. Now, when we use a C-NOT gate on a superposition qubit, we basically entangle 2 qubits together. Why? Because now the state of the second qubit is dependent on the state of the first qubit. So now they are entangled. And this is not a joke. Those 2 gates are the only thing you need on a physical quantum computer to entangle 2 qubits together, and it works. You can do it. You can run it on Azure Quantum. I will show you in a couple of minutes. It just works. It's very easy to do. You only need to do it very quickly, and then it works. If you leave it for an hour, it will never work. But if you do it immediately, it works perfectly fine. But what we basically do is entangle those 2 qubits together, and then we have an additional CNOT gate here to entangle the source qubit to these 2 already entangled qubits. And then we put the message qubit through the Hadamard gate for some magical reason, and then only 2 operations are left. Which is basically measuring or observing the state for the source qubit and the first qubit. Measuring means looking at it and measuring if the result is 0 or 1. If it's in superposition, it will collapse to 0 or 1 if we observe it. That's what the measurement gate does. Now, depending on the kind of superposition, we have those probabilities. It can be 0 or 1 based on the probabilities. But in this case, we first measure the second qubit. We measure it, and only when it returns 1, we will take the third qubit and we will flip it around the x-axis. So we have a couple of gates in the quantum world called x, y, and z, and those gates will just flip a vector around that axis 180 degrees. So the x-axis, for example, if I go back to this slide, the x-axis is this axis right here. It's this horizontal axis. I told you before, the 0 state is up and the 1 state is down. If this black vector is pointing straight up and I flip it 180 degrees around the x-axis, so it will follow this path on the left-hand side all the way around to the 1 state, we basically flipped the qubit from 0 to 1. And if you do that again, it goes to the other side because it always takes the same direction, back to the 0 state. So an X gate in the quantum world is just the NOT gate in the classical world because it flips around from the 0 to 1 and from 1 to 0. Very cool. And then the second operation is we do a measurement of the original origin first qubit. And if that one equals 1, then we flip the third qubit around the z-axis, also 180 degrees, again, which is this axis, this z-axis, which means that if your vector is pointing straight up 0, it just flips around its own axis, which means that it doesn't change position. It just changes orientation. So the remaining state will still be 0, but now there's going to be an imaginary component in the complex numbers and stuff like that. But if you observe it, it will still be 100% 0 state. But this is already weird. We just entangled some qubits. This can be whatever superposition state. It can be like a 31% 0 and whatever we have left 1. And for some reason, when we only take the third qubit and we put it 180 degrees around X and 180 degrees around Z, because all of those are entangled, for some magical reason, now the same state will be teleported until the last qubit. And maybe you're confused now, and that is entirely normal. Quantum is hard. Quantum algorithms are hard. Why? It's another way of thinking. There are a couple of things that are already available, like teleportation. You just need to accept that they work and that we can use them. And now you need all of these little building blocks and you need to use them to build your own quantum algorithms. And that is hard because you need to think out of the box and you really need to know what quantum is all about. You need to know these basic blocks in order to build your algorithms with that. So enough about that. Very quickly, with the couple of minutes that I have remaining, I'm going to talk about Azure Quantum and what Microsoft is doing in the quantum space. Because I already told you a lot of things. I told you quantum is weird, quantum is hard, quantum is even hard to have to use in a stable environment. That is exactly what companies are doing right now. Not only Microsoft, but IBM, Google, universities, countries, Europe, all of us are working hard to build physical quantum hardware, and we hope one day that we can build them on scale, which means we can build them with enough qubits to really solve our exponentially large problems. Today, we're not there yet. We have physical hardware. We can run quantum algorithms on the physical hardware, but they are not scalable. And we can only run very small examples and very small problems that we today can also solve on classical hardware. You probably heard about quantum supremacy. Quantum supremacy just means, can we create a quantum algorithm that outperforms a classical algorithms? Everything we do today, we can also do classically. So everything we do today in the quantum world, we can also do in a classical world, because we are just not there yet. Again, the things work, but they only work on a small scale, and the scale is so small that classical hardware can do the same thing. Maybe it takes a little bit longer, but then again, it costs a lot of money to do it in the quantum world, because we need to cool it down. We need to have sealed labs in order to make that CPU or QPU, quantum processing unit, work. So we should just do it on classical hardware. Maybe in 5 years we have a breakthrough and we can really do these complex problems that we cannot do on classical hardware on quantum hardware. Maybe 5 years, maybe 10 years, maybe 50 years. We don't know, but we are working today on making that happen. And these companies like Microsoft already created the platforms for us in order to do that. So Microsoft is building its own quantum computer, and it's building it based on the topological quantum computer. To be honest, I have no idea what that means. I have no idea what a topological quantum computer is. I tried to read all of the texts regarding that topic, and I just didn't understand. Other companies like IonQ, for example, which is a company Microsoft is working together with, and I will talk about that in just a minute. IonQ is using ion traps. And ion traps are basically ions. They use ions as particles to represent the quantum state. And they use laser beams very carefully to change the superposition state of these ions. So they have a system that works with ions. Quantinuum is another company, another hardware vendor that does the same thing. They also use ion traps. They also have quantum computers that you can use today based on this ion traps configuration. And then there's, for example, QCI, which is yet another vendor of hardware quantum computers. For example, IBM also does the same thing as QCI. They are using superconducting qubits. So they are using electrons and they are using microwaves to, again, very carefully change the superposition state without observing, to basically make the superposition do whatever we want it to do. And there's many more, but these ones are like the largest ones, the most known out there. And what Microsoft is doing today with Azure Quantum is it basically makes the hardware available to people like us, but also people working in universities and really trying to find new quantum algorithms for us to leverage. Now, I'm just going, instead of talking about it, I'm just very quickly going to show you. If you go to the Azure portal and you create a new resource, you can actually search for Azure Quantum. And you should be able to create a quantum workspace. Now, because Microsoft's own quantum computer is not yet finished, they are still working on it. It's not yet stable enough to use, but they are working together with Quantinuum and QCI and IonQ. We can leverage their quantum hardware. So when we select Advanced Create, we can actually do the same thing as with every Azure service, of course, but we can select which providers we are wanting to use. So you can actually select, I want to use quantum hardware from IonQ or from Quantinuum. And there's even another one that I didn't mention, Rigetti, which is quite a new one. But you can select which ones you want to use. And you can do that based on free pricing model, but you can also use that professionally. Today, there's already companies investigating and investing into quantum because they think when quantum is there in 5 years or in 10 years, we want to be ready and we want to build the quantum algorithms already so that we can leverage the quantum hardware immediately when it becomes available. So you can actually do pay as you go and subscriptions. based on that specific quantum hardware. You just select which ones you want to use and which pricing tier you want to use, and you create the Azure service. And what you have created right now is a workspace where you can push your quantum algorithms towards the computer. The quantum hardware will run your quantum algorithms and it will send you the result back. Very easy. It's nothing more than that. And you can use Visual Studio or Visual Studio Code to do that for you. So you can install Q# as a programming language. You can install the Quantum Development Kit, just like you do a .NET project. So I'm creating a new Q# application, and I can choose a console application, for example. And a console application is a quantum application that is simulated on your classical hardware. And the only limit here is the amount of memory, because in order to keep the combined state for all of your qubits in your classical memory, you just need the storage. And I told you, when you add 1 qubit to the system, you need double the amount of storage to store that mathematical formula that represents the state. So for example, this computer that I'm using right now has 32 gigs of memory, and I can do about 28 qubits. If I do one additional qubit, 29 qubits, then it needs 64 gigabytes of memory just to simulate. So we need hundreds and hundreds and hundreds of qubits to do real things, like real problem solving. And that is, of course, not available on your local classical hardware, but also not in the cloud as of right now. So that is your standard console application. You can also do quantum application targeted to a very specific hardware. For example, IonQ. If you do IonQ, you create your project. So let's do Q3. You open your project. You have your Q#. And here you can already see a very small algorithm, let's say. And it looks very familiar if you're using C# or F#. You can see that there's a namespace. You can see that we're adding usings, we're adding other namespaces because we want to use some things from that. We have operations, which is just a method or a function, and it returns a result, which is the result type of this function. So when we run this on physical hardware, we're going to allocate 1 qubit. We're going to put the qubit through the H gate. So we're going to call the H function, put the qubit as an argument, which means put the qubit through the gate, and then return a measurement of Q. So this is basically a random generator. You create a qubit, put it in superposition, measure it, return the result. Now you have a 50% chance of it being 0 or 1, which is now a random generator. By the way, quantum works today. You can build real random generators because you can run that on a physical quantum hardware, and that will be real random, not pseudo random, but real random, because it runs the randomness of nature, let's say. So this is basically what Q# looks like. And as I told you, we are still doing circuits and gates. But of course, you can build functions out of this. You can build a superposition function, put that in a namespace, put that in a NuGet package, and then you can use that NuGet package in your quantum applications. And we are building the higher levels of abstraction by doing these kinds of things, by building functions that already do these gate things, and we can then just call functions instead of gates and build our algorithms on top of that. And with that, I'm just going to slowly start to shut up. To be honest, I can talk 3-4 hours about this topic, but of course it's a Wednesday night, and we have to keep things easy because you have to go back to work tomorrow maybe. There is one example here that I don't have time to show you, but this is a very fun algorithm that I can actually live code to explain where the benefits of quantum can really help us. It's a very fun little game, but I'm just going to skip it for now. I'm going to tell you one small thing, which is during COVID, I got the question from Apris, please, Johnny, could you write a book on Microsoft Quantum? And I told him yes, because I'm just sitting at home at night and I have nothing to do but to watch television. So I wrote this book. If you want to learn a little bit more, you can find it all over the place. You can find it on Amazon or whatever bookstore you like to visit. You can even find it illegally as a PDF if you don't want to pay for it. I don't really care, actually. just if you want to learn, you can look into this and many other options out there. And with that, I can see that there's one question, so I'm very quickly going to read that question while putting this slide up. If you have any more questions after this session, take a look at my GitHub page, reach out to me on Twitter or use my professional email address, and I will be very happy to answer your questions. And with that, I would say thank you. I'm going to very quickly read the question from Leo. So Leo says, as far as I know, classical hardware can't do real randomness. That is true. So how does classical hardware emulate this real randomness? And can it cause problems with programs you write and test on classical hardware? Well, yes and no. So it's very true that classical hardware is not able to produce real random numbers. We have done a lot of research in the past to basically create models that we use to create random numbers that are as random as they can get. So those are basically mathematical functions, like very complex functions. You know, a mathematical function, it's like when you draw it on a graph, X and Y, it goes up and down and up and down. That is actually the base for pseudo-random numbers. When you create a random number, you have probably seen that you have to provide a seed. And the seed is basically where are you going to start on this function. So from left to right, let's take a couple of jumps. That is your seed. And then from there on, you're just going to look at your graph. You're going to draw a point on your graph, and that is going to be your next random number. And then the number after that is going to be higher or lower, depending on where your graph is going. And the function that describes this graph is a function created specifically for this to have us believe that the numbers are really random, but they are not. And that is also the reason why when you have a program that uses a seed, create a random number, when you run that program a week after using the same seed, you will get the same random number, which is not random, of course. So yeah, in quantum hardware, it's going to be real random. In classical hardware, it's basically a faked random. And it can cause problems for very security based programs, because in security, real randomness is very important. But actually, quantum hardware already exists for many decades. And in these very high risk places, we already use quantum hardware that can stream real random data. So that's the idea there. But we can already do that for many decades. So I see one more question from Carol. Probably a question you get a lot, but how close is practical quantum hardware outside of experiments? Well, as I told you, we don't know. We don't know. Many companies are still investigating the different approaches. What particle can we use as representation for a qubit? Today, in classical hardware, we know what a transistor is built out of, so we have that down. We have a good thing. In the quantum, we're not there yet. We just don't know yet which particle we are going to use or is stable enough to use. And there's already something like quantum error correction that we are using today. When a company, for example, tells you that they have 20 qubits available, they have 20 logical qubits, and they have thousands of physical qubits, because they basically run your algorithm in parallel in all of their parallel qubit systems, and they do like an average of the result, and the average of the result is their error corrected logical result. So we are heavily relying on parallelism and doing this multiple times and getting the best result. But we're still looking for that. I know that there's a company in Europe that is looking at things that we can actually use on like room level temperature, that we don't have to cool it down to absolute zero to already help us to do it more stable, but they're not there yet. So yeah, unfortunately, real quantum supremacy is not yet reached. We don't have quantum supremacy yet. Classical computers today are still the best thing we have. John, you're still muted if you're talking.
No, absolutely. I'm just waiting to see if you're going to read through now. Absolutely, superb talk. Thank you, Johnny. I think there was one other thing, which I think we briefly spoke about before we started earlier, Johnny, around, I think it's been mentioned in the chat there. Let me just scroll back out, around the fact that, yeah, people hanging on to encrypted encrypted stolen data, and waiting for quantum computing to do its thing. We see the speeds or the predicted speed for cracking current today's status algorithms, whatever that may be. But
yeah, well,
yeah, I mean,
that is indeed something that really can happen when we find a good physical quantum computer. That is indeed something that we can crack, because this is something that I didn't touch on, but today we already have a large array of algorithms that work in theory, like the math works out. We cannot simulate it because they're too hard to simulate, but the math works out. And there's, for example, the one for encryption specifically is based on Shor's algorithm, so the algorithm from Shor. And you can implement that in Q# today, and you can factorize prime numbers with that, or large numbers into their prime factors with that algorithm. My computer is just not strong enough to do that with significant numbers. I can do it with like 15, and the result of the algorithm will be 5 and 3, which is very cool in itself because the algorithm works in the quantum way, but it's not useful because we can do that from the top of our head. We don't need a computer for that. But the algorithm exists, and from the moment the quantum computer exists that is strong enough, we can just put that algorithm on that quantum computer and it will solve that very quickly.
Yeah, absolutely. No, look, Johnny, can't thank you enough. Thank you for a superb talk. It's definitely one I'm going to be watching the recording on and watching that back a little bit more and doing a bit more of my own investigation. Probably try and purchase a copy of your book as well. So no, honestly, thank you for a superb talk. I'm sure it's one of those areas that everybody's got a little bit of interest in on the sly, but it's great to kind of see it and hear it kind of from your perspective as well, Johnny. So thank you very much for that superb talk. If everybody would like to show your appreciation, whether virtually with the little, there we go, nice one, Carl. Yeah, good to see you, by the way, Carl. Thanks for jumping along. But yeah, thanks a lot, Johnny. We'll catch up. Please feel free, stick around, join in the quiz at the end after Leo's talk as well. But thank you for now. Thanks a lot.
All right.
Cool. Okay. Well, look, thank you everybody for joining throughout Johnny's session there. I hope you'd agree, quite an interesting topic area in and of itself. But look, I'm not going to hold things up. I think we'll move swiftly along. And I'm going to hand you straight over to Leo, and we're going to talk all about Azure Deployment Scripts and running PowerShell. So, Leo, thank you for giving up your time tonight. Over to you, sir.
Yeah, thank you very much for having me. So I hope everybody can hear me. It's always, I guess, again, good. So yeah, I'm going to talk a little bit about how to run PowerShell with Azure Deployment Scripts. First of all, just a little introduction. I'm Leo Visser. I'm from the Netherlands. I work as a cloud consultant, which mostly means that I'm hired to do Google shit. And I do a lot with Azure DevOps and automation, and a lot with Azure infrastructure. You can also find my blog. Hopefully tonight there will be another blog post after this, and you can find me on the socials. And today I want to tell you a little bit about infrastructure as code, just a little introduction for the people who don't know about this. Then what deployment scripts are, when we can use them, how authentication works in this, how we can use input and output, some troubleshooting steps we can do, and in the end, I'm going to show a little bit or tell a little bit about how I use them. And hopefully in between, we have some demos to actually show it if Azure cooperates with me, which is always a scary thing to rely on, but we'll see. So just first, a little introduction about infrastructure as code. I'm sure most of you have some experience with infrastructure as code. The idea is that we have our whole Azure environment, our landing zones, whatever we use, and have it defined in code. This way, we have a standardization of our environment, and this creates a lot less errors. If I need to deploy another virtual machine, I can just use the code I've written to deploy this virtual machine instead of clicking in the portal and maybe misclicking something. It also often reduces the manual labor we're having due to it being a lot easier to automate. Also, a thing which is often glanced over is we have better disaster recovery because our whole environment is defined in code. It's quite easy to redeploy parts or even the whole environment. Of course, we still need to care for our data, but the infrastructure is a lot easier to bring back up instead of having a problem where we need to manually reconfigure everything based on the documentation we probably don't have. And also, it's easier to transfer. So if you need to move the environment to somewhere else, you can use this code to easily transfer it to different places. There's a lot more advantages of using infrastructure as code, and it's been pushed in the communities for quite a while. I think a lot of us have seen the advantages of it and also some of the disadvantages. And it makes us more and more programmers as people who set up infrastructure. Instead of just being somebody who needs to know about infrastructure, we also need to know more and more about these coding things, about how to actually set it all up in code. And there's many different ways to use this infrastructure as code. When we're working with Azure, there are, for example, ARM or Bicep templates. There's also multiple other ways to do it. For example, Terraform is quite popular also because it's platform independent. So you could create a Terraform template for Azure and also use it on AWS or GCP with some minor tweaks, but makes it easier. I will be focusing mostly on ARM in this talk. Nowadays, more and more Microsoft is pushing to use Bicep. I love Bicep, but most of the times I'll be in environments which have been created for the last 10 years, 5 years, whatever. So they were created long before Bicep. So most customers I'm working with haven't yet transferred to Bicep. So this is why I still work a lot in ARM and why I created the demos in ARM. But know that everything we're going to see today is possible in both ARM and Bicep because Bicep will just compile into ARM. But these are just templates. There's some pieces of code we write. And there's multiple different there's also things we can extend this infrastructure as code with to make it even nicer. For example, template specs is something in Azure where we can store our templates directly in Azure, have them be linked together, and be easier to deploy as to use PowerShell or a different language to actually run these templates. Then there's also Azure DevOps Pipelines or GitHub Actions. With these tools, we can create a whole pipeline or a whole sequence of actions which need to be done, where inside we can trigger multiple templates, we can run some code and other stuff. And this way we could create a whole workflow of actually how to deploy an environment. Personally, if I'm working with customers, often we use like these pipelines or GitHub Actions to deploy our whole environments. And lastly, there's something quite new. It's deployment stacks. I must admit, I haven't really been able to play with it that much yet. People who worked in the past with Azure Blueprint might recognize a lot of the features in deployment stacks. As far as I understood, it's like the newer version of Azure Blueprint. And it also allows us to use these templates. In the end, whatever we do, we will be using these ARM or Bicep templates. It's just an extension of the techniques to add even more things to it or to make it easier to work with. So what are deployment scripts? if we're using like an ARM template or whatever, and we're deploying a resource to Azure, we have our deployment, which often goes in a sequence. So there's multiple steps being done, and the resources are being created. So I have a piece of code which says deploy a virtual machine, and it's being sent to the Azure Resource Manager, which ARM stands for, which will then create this virtual machine for me. And in my template, I can have multiple different resources defined. Now, with a deployment script, I can kind of inside this deployment run some code I need and then continue with my deployment. And this is very nice. And we're going to see a little bit later how we can use this. But first of all, let's go into Azure for a bit and just look at some of these things. So I'm now going to share my screen and hope nothing will break down and everything will work fine still. So before we go into Azure, I've got a deployment script or a ARM template over here. Let's make this one smaller. We don't really need it. So for people who've never seen ARM before, the ARM templates are written in JSON, the JavaScript object notation. They have some kind of schema, and then there's an array containing resources. And inside the resources, we can have multiple different resources defined. So in here, we define an automation account. We define some other stuff. And in the end, there's a output block also, so we could get some output back. This is the basic setup of a ARM template. I could use PowerShell to connect to Azure and deploy this template from my local machine. I could use Azure CLI to do it. I could also use the Cloud Shell in the Azure portal to deploy these templates. I personally like to use template specs to deploy it. So if you go to template specs, you can create a template spec, and inside there you can have your template and even multiple versions of it. So for example, I can have my template spec called deployment scripts over here. And I can say deploy or create a new version or edit the description. And I can also see the versions. So in here, I only have one version. I can click on it. I can deploy or edit it. And in here, we have the same template again we saw before. The really nice thing is this editor also has IntelliSense and some checking. So it will validate it. It will tell you if things are wrong. So in here it says, hey, there's something not completely correct. I might have used a version which is not completely supported, but I know it will work. So deploying a template takes a little while. So I'm going to now deploy this template, and then we'll talk a little bit further while this will be running. To deploy it, I have to say where we want to deploy it. So I've created a resource group just to make sure you know I'm not spoofing everything here. Let's quickly check the resource group to see that it's actually empty. So there's nothing in here. And I'm going to deploy it to West Europe because this is still closest to me. We could do a validation and then I can create it. So now it will create some resources for me. It says the deployment is in progress. Some things have been done instantly and it's doing some things. So while we wait for it to deploy, let's talk about when to actually use a deployment script. Because like I said before, we have, for example, these Azure pipelines, GitHub Actions, other things. And inside there, you can easily run a piece of code. You can run a template, run some code, run another template, do whatever you want. But in some cases, you might only be able to use one template file. For example, if you're using template specs to create a collection of templates which people can deploy, because in the Azure portal, these template specs, you can assign permissions to it. You can assign certain template specs only to certain users, so they could use these template specs to deploy certain types of resources, for example. But inside there, you can't create a whole workflow. You could, of course, use tools like Azure DevOps, GitHub Actions, and build it in there. But it also creates a lot more complexity. If you want to offer resources via the Azure Marketplace, you do need to have a template. It can't be a GitHub action unless you use other techniques again. So there are situations where you might want to have it inside one template, or maybe you just like to have it in one template to make it easier to read, because you have a lot of different templates and you're also calling different templates from different templates, and it becomes confusing if you have a big template which creates a complete solution, and inside this solution you have smaller templates doing different kinds of resources, and some of these resources might need a script edit. If this script is not in the template and somebody is creating a new solution, they might add your smaller template not knowing the script needs to be added, and it causes problems. So there's situations where you can only do it in one template file. And situations where you do need to run some code would, for example, to add a delay. This is one of the situations where it's used most commonly. Some things in Azure just take a little bit of time before it's propagated in the whole environment. For example, if you're creating identities, some of you might have noticed this when doing infrastructure as code. If you create an identity and instantly after creating this identity, you want to add some roles to it, sometimes it fails just because you're reaching different servers, you're reaching different things internally, and they might not see it yet. There's other situations where a delay might be useful. For example, if something first needs to synchronize to get some data before it works. Another situation can be that you need to calculate some values. We're going to look at an example of calculating these values a little bit later on in the talk. Or maybe you need to run some additional tasks. This running of additional tasks is exactly what happened inside the template I just shown you. So I'm going to share my screen again. By now, we see that the deployment is complete. So let's go back to Visual Studio Code and actually look at what we exactly did. So I deployed an automation account, but in this solution, I also want to add a specific runbook in this automation account. We're going to skip over this part for now and look at this a little bit later. But here we have the deployment script. So if we're looking in the Azure portal, we'll see that there was a deployment script type of resource called deploy runbook. I'm going to quickly also open up this one in a different window. And this deployment script had some script content and some arguments. Now, if we're going to look at this, this looks a bit weird because ARM needs to have this script on one line. So you will see these /r/n, which are new lines, for example. I've got the script over here too. And this is a script which we were running. So the script had some parameters, and what it did is it checked if we were in the right Azure context, because sometimes you have multiple context and a connection could go wrong. So often you want to make sure that you're in the right context. And then what it did is it took this piece of text, so right host hello world, it stored it into a temporary file, and then it used the import automation runbook command to import this command into, or to import this runbook, this small piece of PowerShell code, into the automation account we created. So, oh, that's the wrong one. Excuse me. So if we look at this deployment runbook, we can actually see in here that it gave us some output. We can also in here see the script which was ran. We can see the arguments which were used. And if we refresh this resource group, we now see there were some things created. For example, the automation account was created. And inside this automation account, runbook 1 was created, which has the line right host hello world. I see that accidentally I did some escaping wrong, so we still have the escaping in here, but doesn't matter for now because this was created in here. Now you might think like I was saying something about I stored a file. I stored a file. Where does this file being created? Well, a deployment script, it's actually a container which is being spun up inside of Azure, inside just hosted resources by Microsoft. And inside this container, it will instantly install the Azure PowerShell and normal PowerShell, and you can run your code there. But it means that you're inside this container. You actually also have access to a file system. So this is why I can say I want to save something into a temp folder and then retrieve this again. That's one of the big powers of these deployment scripts, that you actually have an environment where you can run things in. And there's multiple things you can do with these deployment scripts. So let's get back to the presentation. So these deployment scripts, they are supported in both ARM and Bicep. I've shown you the ARM part, but Bicep also has a support for this. And you saw there was a resource now created in my Azure environment saying a deployment script. But one of the nicest things about these deployment scripts is it has an automatic cleanup. After the time I specified, it will automatically clean up the resources which were created, not the resources altered by the deployment script or anything, but just the resources used to run this piece of code. I can define how long this will take. So for example, I can check, which we will be doing in the troubleshooting also. It has a lot of interesting identity options. And you saw in my code, I gave the script in the ARM template. It also has the possibility to use scripts in remote locations. So I can, for example, say, run this script from this GitHub repository or this Azure DevOps repository. I do need to note it does need to be able to access this repository. And as far as I know, there's no possibility to also include like authentication to these repositories. So they do need to be public repositories to be able to access this. Maybe they've added it since now. The last time I checked was like half a year ago. So maybe this has been added, but as far as I understood, it has not been a high priority. And the AC PowerShell is automatically included. If you want to do anything with Azure, it's nice that this is automatically included and you don't need to install it first. So most of the time you get an environment just ready to go. You can run your code. You can go. So we already looked at the script, but let's look just a little bit more at it. So if we look again at this resource, this is the resource I was talking about, this deployment script. Here it gives us also a timeout, so I can specify how long it will run, and then it will just stop running. We have a provisioning state. There's also a storage account, temporary link to it, and a container instance temporary link to it. And it says already that these resources have been removed. These were only used during the running of the script. So the storage account was actually used to create like some kind of file system, which is persistent for the container instance. And the container instance was used to create this container, which we used. This is all done automatically. I didn't have to specify anything of this inside here. There are some things you can configure. There are, for example, parameters you can configure to have this storage account stay so you can inspect it later. Also here, for example, we have this timeout and this cleanup preference. So here the cleanup preference, it says if you want to have the resource, the deployment script cleaned up afterwards, and I can say after how long it needs to be cleaned up. I believe the 1 hour is the minimum value, so it will always be there at least for an hour, but it's not really in the way. You will just see it in the resource group for a while, and afterwards it will be gone. Oh, I don't need to misclick so much. Let's continue here. So if we're using these deployment scripts, it's nice that we can also use some authentication, because especially if we want to use the Azure PowerShell, we want to communicate with Azure. We want to set things in Azure. We want to alter things in Azure. For example, I wanted to upload a runbook to an automation account. This is not something a user who is not logged in can do. So the deployment scripts actually have managed identities and user assigned identities. So I can create either one. And especially if I use user assigned identities, I can also beforehand assign permissions to them. So when the runbook is running, or when the script is running, it will have these permissions already. So this is what was happening inside the part we skipped over before. So here I was creating a user assigned identity with a certain name, and I was giving it a role assignment, which in this case was a role definition, which is just a certain GUID, but we can look up what this is. Because if we go to the Azure portal, here also our managed identity was created. And we can see what assignments it has. And we can see that it was an automation contributor for this specific resource group. So this is what we did in here. And inside the deployment script, we have the identity part where we say we have a user assigned identity, and we take the name of the identity we created. For people who've never worked with ARM, this looks quite complex. If you've worked with ARM a few times, this is just pieces of code you can just copy paste from everywhere. It's not that complicated to. It's just a matter of getting the name from the identity we created here and pasting it in here and making sure that it works. But we need to do this with some functions in ARM. And this way, this runbook was using the identity we created, and therefore it had permissions to upload this runbook to this automation account. Else it wouldn't have been able to do it, and it would have gotten a 403 error and things would have failed. So this is nice. I had a script and it altered some things for me, but maybe I want to do more with input and output, because a lot of the times I want to give some values to my script, get some values out my script, which I can use. So these deployment scripts have a whole range of input and output options. So let's look at them. Before we look at them a little bit more, I'm first going to create another resource so we can look at this a little bit later. So I'm going to take a different template spec, and I'm also going to deploy this one. And this is the one where I always need to keep my fingers crossed to hope it works. So I selected the resource group again, and the rest of the things, they're automatically populated by default values. I could change them. And while this is deploying, let's look a little bit more at what we did before. So before we had this script and we had arguments. So we had our script content. Our script had parameters. And inside here, we had arguments. We can just enter them as we would do in PowerShell. So we have a dash followed by the name of the argument, followed by the value. I'm using the function concat here, which concatenates the strings together. So we would get subscription ID with a space and then the subscription ID of the subscription used, and so on for the resource group name and for the automation account name. We can also see that this was done in the input. So this is the input it got. Now for output, the one I'm deploying now will deploy a different deployment script. And here we have the script content, and inside we have a variable called deployment script outputs, which is an indexed array, and I use the index text. And here, what I'm doing is I'm getting the current date where I set the minutes to 0 and the seconds to 0, and I add 1 hour to it. So what I'm effectively doing here is I'm asking, what's the next full hour? And I'm converting this to specific time zones to make sure that it's in the right time zone and so on. This variable is a variable which will be recognized by the deployment scripts. And next up, we're going to create a schedule inside our automation account. And here the start time will reference get first hour. Get first hour is this deployment script. It will take outputs.text. So this text we defined here, this is the output of this resource. So this way we can define a start time, because some of you might know that if you're creating a schedule for automating something, the start time always needs to be in the future. It's not allowed to be in the past. So this is a situation where we would need this deployment script. Now let's see. The deployment failed. Of course it failed. Yes. So it failed because Azure is being annoying again. I will explain this later, but I believe we can still look at what it did a little bit. Let me check. Schedules. Yeah, a schedule was still created with the date. Okay. So why did this fail? Job schedules is something I use to connect the schedule which is created to the run book. And inside of Azure, for some reason, these job schedules are global, so they need to have a globally unique, or not global, but they need to have a unique name inside your tenant. In this script I used, the name we created was a GUID based on job schedule 1, and I was testing this earlier today. And I forgot to first delete the schedule itself, and I only deleted the automation account. And if you delete the automation account, it won't delete this job schedule. This job schedule will still exist inside your Azure tenant, but you can't find it anywhere anymore, not even in the Resource Explorer or other things, but it will still be there, and it will give an error where it says a job schedule already exists, and you can't find it anywhere anymore, not even with PowerShell or whatever. This is an annoying bug in Azure, and I forgot while I was testing it earlier today that I had to remove it this way. But for the demo, it doesn't matter, because we still had our deployment script running, and our deployment script was successfully. So our deployment script ran here, and we can check the output, and the output it gave was this. And inside our automation account, a schedule was created, and this schedule starts at 12 o'clock next day. This is due to some time zone stuff and so on, that it's a little bit further in the future than you might think. Also, I'm in a different time zone than probably some of you watching. So depending on daylight saving time and so on, it might be, it's often like 2 hours ahead or 1 hour ahead. This was a bug I didn't care fixing for this presentation. So you see, this way we can also get values into our deployments. Yes, we covered this all. This is just in case Azure is really being annoying. Now, we already saw a deployment failing, but it can also be that actually our script itself is failing. And it would be quite annoying if we can't really troubleshoot this. So let's see what's happening if our script fails. So let's go to Azure again. And let's take the last one I prepared. I'm going to deploy this one. Let's create it. Now we can also look a little bit at how the deployment script is actually created. So if we're going to the resource group, we see it's at the moment still creating the deployment script resource itself. This fail, by the way, that's the name of the resource, though this is not failing itself. Now we see this is being created and it's still provisioning. So this is the containers being spun up, the right data being sent to it, and so on. So the resource is here now, but it's still loading up all the things we need. It's not something you want to use if you need something happening instantly. There's always some time it takes. Luckily, inside ARM templates, for example, if we look at the schedule, we can use things like depends on. So here we had the get first hour, and inside here with depends on, we said get first hour first needs to be completed. The Azure Resource Manager will only say this one is completed once the whole script has run. So this way we know that we can continue. So if you want to add a delay in any way, you could just enter an empty script because this will already add quite a delay. And if that's not enough, you can just add a PowerShell line in here saying wait for so many hours, minutes, or whatever. So now we see it's running and it's trying to execute the script. The script it's trying to execute is blah dash blah. As far as I know, in PowerShell, there's no command which does this. So now it says it failed. And if we look here, it said that our deployment is failed because the script was not able to run. So if our script fails inside the deployment, it will show as a failed resource being deployed. So it will also stop the rest of the deployment. This is something to keep in mind because maybe this is not the behavior you always want. There are ways to fix this. First one being creating a script with error handling so it doesn't fail. So let's open it again. And we can click here on more details. And here we get the full stack trace from PowerShell. So the whole error giving back by PowerShell is being shown here. So this is very nice if you're troubleshooting that you can get the full error. So this is also something I wanted to show you because it happens a lot of the times you're writing this code, then you're testing it locally, it all works, you're running it in a deployment script, and it doesn't work. A lot of the time this is due to permissions, for example, or maybe it's being due to the deployment script using a Linux container and you're testing it on a Windows environment and you're accidentally using some PowerShell commandlets which are not present in PowerShell core and therefore not being able to run on Linux. Stuff like this could happen. So with this troubleshooting, it's very easy to figure out why our script failed. And this brings us to the last part. How did I use these deployment scripts? Well, one of the things I used them for while working for customers was with policy remediation scripts. So you can create policies in Azure, and a policy will check resources if there's something wrong with the resource. And if you can set a policy to do a remediation action, to do something if the resource is not compliant. And these remediation actions, they are just ARM templates. So you can actually, inside this ARM template, again, use a deployment script to run some piece of code. In my case, I had to do some very complex tagging strategies, which I wasn't able to do with just the logic inside ARM. So I created a PowerShell script to get the right information from this resource to determine which tags it needed to have, and then assign this tag to this machine. Another one was that I wanted to have like a start-stop virtual machine solution inside our automation account, but we also had to deploy runbooks which were run on startup and stop. And like I did before in the first example, we were able to deploy these runbooks together with the automation account. So we always knew this automation account had these runbooks. There's also ways with Git integration, for example, to do this, but the Git integration was not a preferred way by them due to how some things were set up permission-wise. So this way we deployed it with the ARM templates and the deployment scripts. That's kind of what I had to show you about the deployment scripts. I hope you learned something about this and maybe consider using them sometimes to tackle some of these nasty problems you have when using infrastructure as code. And I think I saw one question in the chat. I think Ellen had a question about third-party APIs being called. So everything you can do in PowerShell, you can do in this deployment script. As far as I remember, these deployment scripts have access to the internet instantly. If not, you are able to figure this out with some of the settings. So you should be able to call third-party APIs without problems. And a question from D. Your schedule deployment failed because it already existed. Does that mean you cannot use template deployments for updating existing resources based on your new version added? This is a specific thing in Azure where it had some problems. If you pick your name in a better way, you would also always be able to deploy it, and also it wouldn't have failed if I ran it on the same thing, but I was doing it in a different resource group earlier. I was testing in a different resource group earlier today to test if all the scripts were working. So this resource was not exactly the same resource as it was before. And this way, this is why it said conflict. If I had exactly the same version, it would have just worked and it would have updated it. And the last question from Carl. How about using GitHub Actions for your CI/CD pipelines? Are you able to call PowerShell in that platform too? As far as I know, almost every task you can use in Azure DevOps pipelines, you can use in GitHub Actions. I referred to this also at the start. In GitHub Actions or Azure DevOps pipelines, you can do this and split your templates up in different templates and run the code in between. That's a solution, but sometimes you need it to have it all in one template, and then these deployment scripts could be your solution. If you can, I would always advise to try to have it as separate steps in like a pipeline or GitHub Actions or whatever. I think if there's no more questions, I thank you very much, and find me on socials if you want to know more about all this kind of stuff. I blog about these things. I share some information, and hope to see you again somewhere. Thank you very much for listening.
Thank you very much, Leo. Awesome session. Thanks for taking us through that again. Some really great information on there. Again, another one I think I'm going to be personally watching back for a little bit of time. So no, some great info in there. So yeah, everybody show your appreciation for Leo. Thanks again to both Leo and Johnny for giving up your time tonight, and obviously taking us through some awesome topic areas again, as I think we always seem to be getting now. So thanks, guys. Really appreciate it. Everybody stick around. We'll move swiftly into the quiz. I appreciate we're kind of timing out now at 8:30, but I think 5-10 minutes we should be able to whiz through the quiz quite quickly, Matt, no doubt.
Yep, hopefully.
Get
We're going to do top one tonight, top winner.
Yeah, I think so. Yeah, how many we got? We got 12, 13. Yeah, top one.
Let me stick a share on.
So we'll have a £25 Amazon voucher up for grabs. So everybody wants to go to the link, and I'll let you take over.
There we go. And fingers crossed, thank you, Nicholas, for your vote of confidence. It'll all work tonight.
I mean, we say it every month, but for those interested, this quiz platform is a bit of a, well, it's a version of other well-known quiz platforms, I suppose we'd have to say. Take a look. When did you do the talk, Matt? It was a little while back.
March last year, so March 22. March, April. So yeah, it's a .NET project. So it's a .NET Signaler experiment. Bobby drop tables, nice. Thank you very much. Someone's trying to break my system as well. Yep, it's all available on Git. We can send a link over. I can drop a link into the chat at the end.
Yeah, it's on Git.
Anyone struggling to get in?
How many we got? We got 5 on there. How many more? Anybody struggling? There we go. There's
Another one.
It says a join, but I don't see myself on your screen. Try it again, Nick. Refresh your browser. D is on his screen, but not on ours.
Try refreshing and try again.
Yeah, try again.
Literally the have you turned it off and turned it back on again solution for the modern era.
It's not working for me. I'm going to try on my phone.
Okay.
Yeah, give it a minute or two.
Wish I knew why it didn't work for some people. It's very frustrating. No, I've had D says is 6 the limit. I've had it up to about 150 people on. That's the beauty of Signal.
One thing, just for anybody that's never used it before, it does take a little while to load first time round.
It's a downside of using Blazor WebAssembly, which is the technology behind it, is that it has a fairly chunky download initially.
So I'm in on my phone, but not on my computer. Although it is my work computer and it uses Zscaler, so maybe Zscaler is the culprit.
It's probably a WebSockets problem in that case. That's interesting. That's interesting to know, actually. Yes,
I've had that problem before on this computer. So
yeah, the new Blazor Unlimited or Blazor whatever it's called now, the stuff that's coming in .NET 8, really, really good, really interesting. Anyway, I'm going to kick this off now. D, you still trying to get in?
Yeah, I'm in now. So
new browser, same problem.
Same problem.
Yeah, .NET 8. I'm amazed, astounded that there even seems to be performance improvements in .NET 8 again, which I don't quite know where those are coming from, because there's been performance improvements in literally every version from 5 onwards. And not insignificant. There we go. Right, I'll kick that off now. Right, so I hope you're all paying attention during Johnny's quantum session, because there's a lot of quantum questions in there. Hope you all know your entanglement from your separations. So let's start with which Azure camera hardware was discontinued this month? For the second time, we've discontinued Connect. This is the Azure Connect, this time, unfortunately. What's the compute resource that powers deployment scripts? Answer is container instances. Other than PowerShell, what other type of deployment scripts are supported? Yeah, Azure CLI. Well done. Majority of you getting that one. Oh, interesting one. Which of the following is not a supported QDK language? Now, I had no advance warning on what Johnny was going to cover, so I've randomly picked some quantum questions. The correct answer is Java. Oh, only one of you got that one. What's the name given to a basic unit of quantum information? Qubit, a quanta, a quickie, or a Q? Well done. Which of the following cannot be used to deploy resources to Azure? I'm guessing that's going to be a 50-50 for most people. Lang chain's the right one. Oh, more of you got that than I thought. How much is M365 Copilot per user per month? And it's cheap at half the price. I have to say that as a Microsoft employee. It's $30 a month per user per month. Oh, how much disk space is Starfield going to require on Xbox at launch? Which is this weekend, I'm hoping. I get it unlocked. It's 100 gig. Which Azure service celebrates its 10th birthday this year? Now, there was some debate about this. It's the artist formerly known as AAD. It existed in other forms, sort of, before that, but officially as Azure Active Directory, that was its 10th birthday. EID is so much better. Yeah. I don't know, the debate's still out on that one. Which new blob storage tier is now generally available? I love the idea of there being a lukewarm tier.
An Inferno tier.
Yep. Only available for Disco. There we go. Oh, John, you've won again. But
I win now. I don't know why you say again. I very rarely win. Yeah, obviously I'm not going to take that. Who's second? Is that Al, is it?
Al, yeah.
There we go, Al. God, he's becoming a regular winner now, Alan. We're going to have to do something about you. Get some curveballs in there.
Yeah.
That is Florence, isn't it? Alan Florence, just to make sure there's no other Als.
I got quite a few of those wrong.
Yeah, I did as well. But
so there we are. By the looks of it.
There we go. That's the way it goes. But well done, Al.
Misclicks.
Yeah. Well, no, there are a few curveballs in there, Matt. Good quiz again, as usual.
Yep.
No, well done, Al. I'll get that sorted out for you. £25 Amazon voucher. Where you'll be able to give Jeff Bezos a run for his money, the amount of vouchers you're collecting now. So, no, well, right, okay. Quickly then, I'll quickly close off this evening. If I just get the old slideshow back up and running, just so we can get the feedback. Bear with. Caller, right, there we go. Hopefully you can see my screen now. But yeah, look, thank you all for joining. Really appreciate everybody giving up the time and coming on and learning something new this evening, joining the quiz, and seeing some familiar faces. Really is appreciated to support you guys who kind of join the group. Huge thanks to both our speakers this evening, Johnny and Leo. I hope you agree. Two great sessions again from some great community speakers. So yeah, huge thanks to those guys for giving up the time and coming on and saying hello. Matt, thank you as always. Great quiz again.
My pleasure.
And and I guess with that, we're still not getting back to in person. So I think we're still going to be virtual next month. So we put it a week later. We're usually the third Wednesday, but I think because of the lots of holidays this month, we're a bit later this month. I think we're naturally going to be a little bit later next month as well, purely because there's so much going on. So we'll more than likely be back virtual on the 27th. Yeah, absolutely, Carl. I think this is the way of the world still for a lot of people, isn't it? So we'll be back 27th September. Put it in your diaries for now. We'll get the sessions up on Meetup soon enough. If you can join that QR code and drop us some feedback, give us any feedback on talks, or if you want to join in, if you want to come and give a session yourself, there's links. If you follow those links and go onto our socials to the Sessionize page. Is there plans? Yeah, absolutely. I think me and Matt have talked quite a lot about kind of pulling together, a hybrid / we want to get back to in person. So whether we do it kind of on a quarterly basis and keep virtual in between, we've thrown around a lot of ideas. But yeah, for everybody that's kind of in and around Bristol and South Wales, absolutely, we want to kind of get that. So I think hopefully we can get the momentum. We can get a good kind of, at least 10 to 15 people in a room. Watch this space. Yeah, no, I know what you mean, Carl. It's only over the water, isn't it? It's not too far, but it's far enough. But yeah, so
that's 5 hours for me.
how long is it?
I reckon it's about 5 hours to get down to yours. I'm only guessing.
You're way up north for you there, Al. But no, exactly. And I think we've got a good core of people, and not everybody joins every month as can be expected. So we're keen to keep it virtual. I'd like to think we could do the hybrid piece if we go back to in person. But yeah, watch your space. I think both myself and Matt have been we've gone through job changes, and of course there's lots going on. We've had holidays and all sorts, so it's just been one of those things. I'm sure we can all appreciate just time is quite limited, I think, for a lot of us at the moment, but we're going to keep on going.
Look on the bright side, it'll be just after the next round of vaccines start.
Oh, don't
You're all
I'm not
cheery,
joking. 11th of September.
Yeah, I think there is.
Have you not heard that one?
I like Dee's suggestion to drop the Welsh part. We can't drop the Welsh part. That's just not, that can't happen now. We've been Welsh Azure user group for too long now.
We've got a cool logo and everything.
We have. We've got a dragon's claw on a cloud, for goodness sake. It's. But
why would you want to use the Welsh part?
Well, because it's more of a global European / global kind of.
Oh my! It's still where it emanates from. That's its essence.
There we go. There we are. No, I'm sure we will. We'll find a way. But yeah, we'll find a way. But I don't think we'll ever go.
Okay, in that case, make it the global Welsh Azure user group then.
I was being facetious.
See what you've done
from a fellow Welshie as well.
Or the Quantum Welsh Azure user group. There you go.
Sounds like just coming on here.
Just say the Welsh, as in SHA 256 Azure group.
Oh no!
Oh, well done.
Oh dear. The Welsh SHA, nerdy, technical, geeky. Right, we're going to call it there then on that bombshell.
Yeah.
You'd have to be at least SHA 5112. Come on, it's secure.
Thank you very
Cheers.
much.
Bye.
Right, thanks all. See you all soon.
See you soon.
No worries.